So we have two athletes compete in a 2-event competition: shot put and the long jump. Chris threw the shot put 63 feet and Ryan threw it 66 feet. Chris jumped 27 feet 3 inches in the long jump, and Ryan jumped 27 feet. Is Chris or Ryan the better athlete? So I'm just sitting there trying to figure out how you can jump 27 feet. Like, that just seems like...
It's a tough thing. It's like a running start.
Yeah, but still. That's like longer than this.
27 feet.
Or, well, it's probably like from that wall to...
Yeah, well, I know I couldn't do that, so here we are.
So when we're looking at this, we want to think about which athlete did better compared to his peers. So we're going to use standard deviation to show how far the value is from the mean. And that's going to just help us to standardize the values to know exactly what we're working with. So, does it not give you the, oh, why is that not filled in? Hold on, this stuff is supposed to be filled in for you. This mean is supposed to be 60 feet. I'm sitting here and I'm like, something's missing. 60 feet with a standard deviation of 3 feet, and then the long jump is 26 feet with a standard deviation of 6 inches or 0.5 feet. Yeah, I was sitting here and I was like, there's no way we can do this problem right now. And then I was like, oh. Why did I not fill those values in the chart? Who knows? So then just a reminder, z-score is y minus y bar over s for standard deviation. So we're going to do basically Chris and Ryan for both things. And then we're going to do it for shot put and for the long jump. So, what is the formula filled in for shot put for Chris? Yeah. It'll be 63 minus 60 over 3, which is just going to end up being 1. So he's 1 standard deviation above the mean. And let's go ahead and do his long jump. So what goes in that one?
27 feet and 3 inches. Wait, so 27. No.
27.25. Yeah.
27.25 and then 26 minus 26.
Yeah. And because we're dealing with feet, that's why we needed to convert from 6 inches to 0.5 feet. Oh, okay. I thought you said it and I just missed it, so I was like, wait, I need you to say that again. Please.
1.5.
What you said?
Should be 1.25 over 0.5.
minus 26.
Oh, yeah, that makes sense. I was subtract. Never mind.
You did it
Ignore what I
backwards?
said. Yes.
I got negative 24.75.
Well, it shouldn't be negative.
Wait.
27.25 minus 26 should be 1.25 divided by 0.5.
Minus 26
Divided by 0.5.
equals divided
I got 2 points.
by.
Okay, yes, that's right.
I'm kind of stupid, but here we are.
Hey, this is the time to make the mistakes, right?
Yeah, our test.
All right. And then for Ryan,
He did 66. 66 minus 60 over 3. That would equal 2.
and his long jump,
27 minus 26 over 3. Should be
27
so which athlete did better? Like, look at both things.
Hold on. Yeah, Ryan.
So, but like look at both things like together. So like on average, who did better?
Ryan.
So Ryan is the better athlete.
Sweet.
All right. What? Oh.
Your staples in this one?
I put some in it the other day, so probably, but it's never a guarantee these days. All right. So these ones are actually really easy. So a statistics class took a 40-point quiz. Results show a mean score of 30, a median of 32, an IQR of 8, standard deviation of 6, min of 12, and Q1 is 27. Suppose your score is a 35. So we plug in the numbers, so the statistics that we start with, so the original Y value, okay, it's going to go there. So then what happens to each of the statistics if I decide to weight the quizzes as 50 points, and we'll add 10 points to every score. So first let's fill in this top. So our score was a 35. The mean value was 30. Median was 32. IQR of 8. Standard deviation of 6. Min of 12. Q1 of 27. So if I want to weight it as 50 points and I'm adding 10 points to every score, what am I like changing about Y, the Y value?
You're multiplying by. Oh, wait, no.
If it was 40 point, now it's 50 points. What did I do?
You're adding 10.
So the statistic is Y plus 10.
So did you just add 10 to everything?
No.
I was about to say that would make sense.
So we add 10 to your score, so you got a 45. We can add 10 to the mean, so that's 40. The median, we can add 10, so that's 42. Skip IQR and standard deviation for a minute. The min is also going to get 10 added to it, so that's going to be 22. the Q1 is going to also get 10 added to it. But the thing to note is that if my Q1 gets 10 added to it, that would mean that what is happening to my Q3?
Oh, wait, your Q3 is getting bigger.
If I added 10, it's also going to get 10 added. So if I had, yeah, so the IQR is going to stay the same. When you're adding, IQR stays the same. Standard deviation, for a similar reason, because everything's changing by the same amount, is also going to stay the same. Down at the bottom of your page, you see where it says summary. We're going to go down there and we're going to note a few things before we do the next two, so that you kind of already have the information that goes with it. So all right, so when adding the same number to every value, okay, so like we just did in the first one, it changes the center and individual values. Okay, so that's talking about like your mean and your median. But like we talked about, because it's changing everything by just adding 10, your IQR and your standard deviation isn't changing. So while the center changes, the spread does not change. So, but it doesn't change the spread, which is your IQR and standard deviation. I think they have those written backwards for what they go with in the previous one, but now that's if you're adding, but sometimes we also multiply. So for multiplying every value by the same number, when you do that, it does change. It changes the center and individual values. Okay, so that's still your mean and the median. So if it said that we're gonna take the 40-point quiz and we're gonna make it out of 120 points, okay, you multiply everything by 3. Okay, your mean, median, all that stuff. But the difference with this one, with multiplication and addition, is that it also changes the spread. Your IQR and your standard deviation. So when you multiply, it changes everything by whatever the factor that it's being changed by. When you add, it changes everything except for your spread. So it changes everything but your IQR and standard deviation. If both things occur in the same one, because that's what we're going to see in this one, if you have multiplication and addition, you're going to do the multiplication first, then you're going to do the addition. So just like PEMDAS, like you would normally do. So what happens to each of the statistics if I decide to weight the quizzes as 80 points and double each score? So again, we would just copy down the original set of numbers that we had.
So it would be y times 2.
Yep. So we have 2y. So then what does that give us going across?
70, 60, 64, 16,
Long day.
Really though.
All right, so then the next one, what happens to each of the statistics if I decide to weight the quiz as 100 points? So you're doubling each score and then adding 20. So again, we copy down those values that we started with. So what is the equation?
2y plus 20.
Yep. 2y plus 20. So you're gonna multiply by 2, then add the 20 for everything except IQR and standard deviation. For those, you're only multiplying. We don't do the addition. Yeah. So that's gonna be 90, then 80, then,
And then 16 and 12.
yep.
44.
Yep. So see,
Oh,
those
that was
ones,
easy.
those ones aren't that bad. And typically I do end up putting one of those on the test for, you know, some easy points.
You gotta do it like right.
What?
You gotta do it like right.
No, I just, it's because there's pictures.
Oh, you have to show the end of that.
All right, so Martha scored 80 on a physics test where the mean was 75 and the standard deviation was 5. Bob scored 83 on a chemistry test where the mean was 73 and the standard deviation was 12. Who scored the highest relative to the rest of his or her class? Show your work and defend your answer. So, just to have a quick little picture here. Yeah. Martha. And then we're going to have one for Bob as well.
That was a terrible curve.
Yeah, mine are, you know, there's some things like that I get pretty good at drawing. This just has never been one of them. So the mean for the class is what is going in the middle of your graph there. So in this case, the mean for Martha's class was 75. The mean for Bob's class was 73.
But the standard deviation was 5.
So the standard deviation was 5. Since that's what she got, I'm only going to put the 80 on there. For ignore what I was about to say. The standard deviation for Bob's class was 12, so I add 12 to that, so that's 85. But we do want to note that he got an 83, so I just am going to put a little tick mark on here to show that he had an 83 rather than the 85. Okay, so just from the picture you can probably see who did better, but to see it mathematically, what would my z-score for Martha be? Yep. And that's just going to be one standard deviation. And then what about the z for Bob?
83 minus 73 over 12.
And what does that end up being? Which is what? In decimal?
Yep.
So, who did better relative to their class?
Martha.
So just all you would need to have for a write-up for this is that Martha did better relative to her class. Her score was 1 standard deviation away from the mean. Or I guess you should say above the mean, technically. Above the mean. But Bob's was only 0.83 standard deviations above the mean for his class. Oh yes, the next one's about cows.
It is.
Should bring in Gerald for the event.
She got last year. She got cows and pigs and monkeys,
The pigs are actually for this class.
and the monkeys, all their heads fell off. It's this whole thing that none of the monkeys have their heads anymore.
Stress cows.
Yeah.
Also, the guy that I got to feed one of his cows, one of them is actually named Gerald.
That's so funny.
I was like, it's a sign.
Yeah, we have a Gerald too.
I told him that. I said, he probably thinks we're crazy,
Yeah.
but whatever. All right, this one happens to be number 17 in your book. Just FYI if you care. The Virginia Cooperative Extension reports that the mean weight of yearling Angus steers is 1,152 pounds. Suppose the weights of all such animals can be described by a normal model with a standard deviation of 84 pounds. How many standard deviations from the mean would a steer weighing 1,000 pounds be? So we just need to find the z-score with the given information. So what would that be for this one?
Okay, so 84 is on the bottom.
Yep.
And then
Would be 1,152 minus 1,000.
I was about to say the other way around.
Flip it.
because
You have
the
your
mean
actual
is
value
yeah.
minus the mean.
Oh yeah.
So 1,000 minus 1,152 over 84.
Wait, can the z-score be negative?
Yes. A negative value is going to indicate that it's below the mean.
Oh wait, I did divide it by. Negative 1.81.
Negative 1.81. And so to write out what that means, we would say a steer weighing 1,000 pounds would be 1.81 standard deviations below the mean. Okay, so we don't need to put the negative sign if we say below the mean. That's why we specify if it's above or below. When you show the math, you should still show the negative sign in your math, like we did up there. But then you would say that it's below the mean when you actually do your little write-up about it. So then part B, would it be more unusual to see a steer weighing or 1,000 pounds or one weighing 1,250 pounds? So you've already done your z-score for 1,000 pounds, and that's minus 1.81. Okay. We need to do it now for the 1,250 pounds. So
So it's just which one is farther away from?
yeah. And it doesn't matter above or below. We're looking for the number, basically the absolute value of the number, essentially. So which one is farther away?
Okay, so it's 1,250 minus 1,152 over 84, which is 1.17.
So this one is 1.17. So which one is more unusual? The 1,000, because it's farther away from the mean. So the steer weighing 1,000 pounds is more unusual because it is farther from the mean than the steer weighing 1,250 pounds. Alright, we'll go ahead and do the next problem, and then that's where we're going to stop for today probably because the next stuff is calculator, and I'd rather do all the calculator stuff in one day. So, they're not, like, these aren't bad though, they're not. Alright, so the Environmental Protection Agency, EPA, fuel economy estimates for automobile models tested recently predicted a mean of 24.8 miles per gallon and a standard deviation of 6.2 miles per gallon for highway driving. Assume that the normal model can be applied. So then first we want to draw a model for auto fuel economy, clearly label it showing what the 68, 95, 99.7 rule predicts about miles per gallon. So what you want to do here is you want to have your curve, I can't think about it that much, I just have to do it. And then you want to go through and you want to label.
It's on 6.2 applied, right?
Yeah. So you're going to start with 24.8, and then you're going to count up by 6.2, and then count down by 6.2 until you're 3 standard deviations away. So like your next one would be 31, then the one after that would be 37.2, and then your last one would be 43.4, and then you do the same thing working backwards. So it would be 18.6, is that 12.4, and 6.2. And then it just wants you to draw the region where you have each percentage. So for the 1 standard deviation away, it wants you to show the 68% is there. 2 standard deviations away is 95%. And then 3 standard deviations away is your 99.7%. And your label for the bottom should be highway mileage in miles per gallon. So then having that will allow you to answer the next few questions that come up with it. So in what interval would you expect to see the central 68% of autos to be found? 18.6 to 31 miles per gallon. What percent of autos should get more than 31 miles per gallon? So, 31 miles per gallon, okay, is in the 1 standard deviation away, right? So it's 68%, right, is in the 1 standard deviation away. Oh. So we need to do 100 minus 68, okay, to see we want more than 31 miles per gallon. That's going to help us to see what's outside of that region. Okay, so outside of the 1 standard deviation away. But I only need the half that's above, not the half that's below over here. So I need to cut it in half. So you're going to have 100 minus 68, and then we're going to divide that by 2.
16.
So then that's going to be approximately 16%. Okay, obviously give or take a little bit. I know it's a little bit weird, but it's like you have to remember like what chunk of your data are you like looking for. Like if it just said what percent of autos would you expect to be more than 1 standard deviation away, we would just be doing 100 minus 68, and then that would give it to us. But this specifically wants the upper part that's more than 1 standard deviation above the mean. So we have to subtract off the 1 standard deviation and then divide that in half to get rid of the left side. So then with the next one, about what percent of cars should get between 31 and 37.2 miles per gallon?
Roughly 8.
How'd you get that?
Okay, well, you would take the 16% that you had and then divide it again.
Sort of, but that's not going to be the exact percentage that's in there. Because you have to remember, there's technically stuff that's more than 3 standard deviations away. So this one, so 37.2 is 2 standard deviations away. So I'm going to use 95.
Instead of 100?
Mm-hmm. Because that's my upper limit, because it wants it between these. So I'm using 37.2, which is the 95%. So I'm going to have 95 minus 31 is at 68%. So I'm going to take off the 68%, which would give us the stuff that's between 1 and 2 standard deviations away on both sides. So I need to cut it in half again.
13.5.
And that's, again, it's an approximate, because obviously it could be a little bit off, but 13.5%. So describe the gas mileage of the worst 2.5% of all cars.
So, that is 6.2. Or is it less than that?
Actually, more than that. So think about when it's talking about 2.5, that's half of your graph. So if you multiply 2.5 by 2, what do you get? So 5%. So how many standard deviations away are we looking at? What percent up there plus 5% gives you 100%? 95, okay? So we're looking at the stuff that is below that percentage away, because there's 5% left, so that means there's 2.5 on each side, percent-wise. So the worst 2.5% is going to be anything 2.4 and below, 12.4 and below. So it'd be 2.5% times 2, which is your 5%. So that tells you that we're looking at the 95% or 2 standard deviations away. So it's going to be approximately less than 12.4 miles per gallon. So what should you consider to be unusually high miles per gallon and unusually low? So how many standard deviations did we say we consider unusual? Anything more than what?
I have no idea.
2. So if it's more than 2, so we would say 2 standard deviations from the mean is considered unusual. So with that being said, what is an unusually high?
Less than 1. Lies. Ignore what I said. That's
Like what miles per gallon would we consider unusually high?
37.
Okay. So 37.2 miles per gallon or more. Because technically, like I said, there is stuff that's way farther away than 3 standard deviations. It's just when you go beyond that, it's only 0.3% that's beyond that. So it's just like not worth, well, technically it's not even 0.3 if you're just looking at the top half. But there's more that's beyond that. So we always say like or more. And what about unusually low?
6.2.
Are you sure? 12.4. 2 standard deviations away. 12.4 miles per gallon or less. All right, so the next set of problems, like I said, we're going to go ahead and stop because they're only about 5 minutes, so we would not get through the entire next problem, and it's going to be some stuff on the calculator, so I'd rather just try to do that all at the same time. Hopefully we'll finish up examples tomorrow. I'm assuming y'all don't want any problems to start with at this point.
No.
So, all right.
Yeah, these four stuff is cool. It's just
That's what we just did.
It definitely takes like time to like get used to it. Like it's just one of those things that it's like doing it several times and eventually like it starts to like make sense. Like why you have to split stuff in half and like all kinds of stuff like that.